Okay, hello everyone, in a new video. So we have reached part 3 of chapter 6, which is the chapter of AC voltage and the second unit of electricity. And eventually we have reached section number 13, which is the oscilloscope. Then let me write down here section number 13, the oscilloscope. Then previously we have mentioned several times the oscilloscope, and we have used it several places in our calculation, whether in the chapter of the DC voltage or the AC voltage. And now we are going to see the oscilloscope as an instrument. So this is the oscilloscope. This is the screen of the oscilloscope in which we observe the waveform. So in this case, what's the type of this voltage? So it is an AC sinusoidal voltage because it varies with respect to time and it's alternately positive and negative, and the shape is sinusoidal. So this is the graph. As for the divisions along the x-axis is made up of 10, and the divisions along the y-axis is made up of 8. Okay, and we can count the number of divisions along the x and the number of divisions along the y. So this button here, the on off, is the one responsible for switching the oscilloscope on and off. So this is the adjustment in which we have seen previously before we use the oscilloscope, the luminous line. So in this case, this is the luminous line, which is have the same the shape of the sinusoidal. It must be adjusted to the center of the screen. So this button is responsible for adjusting this shape at the center of the screen. Now yet we didn't discuss the sweeping, which is the title of the next section. What about these? So here we have connecting wires. So this is the phase terminal, and this is the phase or the channel, and as for this case, this is the mass or the ground. Yet we have two other properties of the oscilloscope that are given by the SV and by the VB or SH. So we know that the unit of SV is given by volts per division, and so it's related to the voltage. And as for VB or SH, it's given by seconds per division, or related to seconds or milliseconds. So noticing that here these are the two knobs. So if we consider the first one, which is down here, they are telling me volts per division, which is the unit of SV. So by moving the knob like this, rotating it like this, or even like this, we can adjust the value of SV from 0.1 up till 10. And as for this one, so this is VB because it's given by time per division, which is the unit of SH or VB. And by moving the knob like this, or even like this, we can adjust the values from 0.1 up to 10. So this is the oscilloscope. What about this button, which is the sweeping, which allows us to move to the next section? And the title of this section is given by the sweeping, which is section number 14. Now for the time being, for the purpose of this section, let's ignore this row, and let me consider only the second row, which we are familiar with. So notice that if we now discuss this one, this is a 0 voltage, so a luminous line at the center of the screen. So here we are discussing in the first column of this table the DC voltage. So if the luminous line is displaced upward, so this is a DC positive voltage. If the luminous line is displaced downward, this is a negative DC voltage. So this is in the case of AC voltage. Now in the case of AC this is the case of DC voltage. Now in the case of AC voltage, if we have 0 voltage, then the luminous line will be at the center of the screen. Now in the case where we have voltage, then the voltage, for example, on one of the cases will be something like this. All of these cases that we have discussed are in the case where the sweeping is on. So now what happens? So this in the case where this button is switched on. Now suppose that we switch this button off, what will happen? So let's consider the following case. Okay, before discussing what will happen, what is sweeping? Sweeping is the motion. So sweeping as if something is moving from left to right or right to left. Okay, this is what is meant by sweeping. So notice that previously in this case, this is a luminous line when the sweeping is turned on. The moment we switch the sweeping off, instead of observing a luminous line, we will observe a just luminous spot. Then we will observe a luminous spot at the center of the screen. Why? Because whenever we switch the sweeping back on, this point will sweep, which will move like this. Will move from the left to the right, will move from the left to right. Because it's moving at a very high frequency, then instead of observing a point, we'll observe a line. Okay? Similarly here, in this case, the sweeping is on, which means that the point originally is moving from left to right very fast. When we switch the sweeping off, so this point will be steady, will be here, and will not move anymore. For this reason, instead of observing a luminous line displaced upward, we will just observe a luminous spot displaced upward. Because this line is displaced downward and we observe a line because the sweeping is on, whenever we switch the sweeping, we will observe only a luminous spot which is displaced downward. Now in the case of AC voltage, this is a bit tricky. So in the case where the voltage is 0, so when the sweeping is off, we will just see a luminous spot on the center of the screen. But what about in the case of the AC voltage, this one, whenever we have a voltage, so we know when the sweeping is on, we will observe a waveform which has the shape of sinusoidal. Now so this is in the case where the sweeping is on. Now when the sweeping is off, what will happen is that now we will observe a luminous spot. Okay, but here in this case we cannot say that the luminous spot is displaced upward or downward, because it's an AC voltage, so it's be positive or negative. So at some point, for some period, the luminous spot will be displaced upward, will go up, then for another period it will go down. So it will go up and down. Instead of being displaced or swept in the shape of a wave, it will just go up and down. The luminous spot will only go up and down, and it will not move left to right or right to left, because the sweeping is a switch off. It will be only moved up and down, up and down. In this case, what we will observe is a luminous segment along the vertical axis between y and minus y. Now it's a bit difficult to imagine how this luminous segment is being observed. So you can try to understand it, but what I want from you is that whenever we have an AC voltage and the sweeping is switched off, just to memorize that instead of observing a waveform, we will observe a luminous segment along the vertical axis between a plus y and minus y. Then we have reached section 15. And the title of this section is Electric Power in an AC Voltage. And as we have discussed previously, that every notion that we have passed over, or almost all the notions that we have passed over the DC voltage can be discussed in the case of AC voltage, and in this case you are interested in discussing the electric power. So previously in the DC voltage we have seen that the formula of the electric power is given by P is equal to U multiplied by I. Now, how this formula can be generalized in the case of AC voltage, because we know that in the case of AC voltage we have two voltages and they are given by UM and U effective, but in this case we always consider U effective. Okay, so now let me write down, consider an electric component D. Fed by an AC voltage U. And now we are interested in defining the electric power in the case of an AC voltage. Then let me write down the electric power of D is given by So we know that in the case of DC voltage, P is equal to U multiplied by I. So in the case of AC voltage, this will be simply given by P is equal to U effective, because U is the voltage that's making the effect. What about the current? Because this carries the label effective, then eventually the current will carry the label effective. Okay, so let's write down P is equal to U effective multiplied by I effective. And for any formula in physics consisting of three variables, we can construct the triangle. So this is the triangle. So notice that here, because we have multiplied, and P will be at the top, U effective, I effective at the bottom. Okay, suppose in this case you are interested in determining I effective. So the definition or the formula of I effective is simply given by P divided by U effective. Okay, and notice that in this case U effective and I effective are neighbors living in the same floor. So then in this case they hate each other. If U effective increases, eventually I effective decreases, in which P kept constant. And now let me discuss the units that we already know, and let me say where. Then P is the electric power consumed by D, and we know that the SI unit of power is given by watts. So W is the symbol of watts, which stands for watts. Now as for U effective, we know it is the effective voltage of D, in which we are calculating the electric power of the component D. Therefore U effective represents the electric power of D, and its symbol is volts, which stands for volts. Now as for I effective, is the effective current of D, and its unit is given by SI unit is A, which stands for amperes. So this is it basically, the electric power in the case of AC voltage. And for example, if you want to discuss Ohm's law in the case of AC voltage, so we know that in the case of DC voltage, Ohm's law is given by U is equal to R multiplied by I, and this can be generalized in the case of AC voltage simply by replacing U by U effective, which is equal to R. R doesn't carry any label because it's always constant, and in this case I will be the I effective. Okay. And now let me solve the following exercise, which is exercise 5 section 16, as a direct application on what we have explained. So they are telling me an electric component D consumes an electric power P is equal to 100 watts when fed by generator U delivering an AC sinusoidal voltage UM is equal to 112.8 volts. So as we know that whenever we have P and U, so it's logical that by knowing the nature of the voltage, we can determine the value of I, because in general P is equal to U multiplied by I. If the type of voltage is AC, then this will carry the label effective and this will carry the label effective, okay? And whenever we know UM, U effective can be deduced directly. So, and take square root of 2 is equal to 1.41. And number 1, they are telling me calculate the effective voltage, U effective of D. So here notice that the type of the voltage is AC sinusoidal and we know the maximum voltage. Therefore, we can directly determine U effective because they are related to each other via the following formula. Now, the value of UM is given by that. And here, radical 2, we need to use its approximation, which is given by 1.41. Now, plugging this fraction on the calculator, we get that the effective voltage is given by 80. Since UM is expressed in volts, so the U effective will be expressed in volts. So in this case, U effective is equal to 80 volts. Now, as for number 2, they are telling me deduce the effective current, and by deduce, it means that we need this previous part. In the previous part, we have determined U effective. We know that I is related to U either by Ohm's law or across the power. Here we have the power. So let's say P is equal to U effective multiplied by I effective. And if we construct the triangle of this formula, so here because we have multiply, then P will be at the top, U effective and I effective will be at the bottom. We are interested in determining I effective, so putting our hand over I effective, which is equal to P divided by U effective. The value of P is given by 100. The value of U effective is given by 80, and this is equal to 1.25. Since P and U are expressed in the SI, so the value of I will be in the SI, which is amperes. Then I effective is equal to 1.25 amperes. And now moving to the next exercise, which is exercise number 6. They are telling me an electric component D is fed by generator U delivering an AC sinusoidal voltage UM is equal to 310 volts. Now, given I effective is equal to 0.5 amperes and take square root of 2 by this decimal value. Now, if you notice that once we have UM and the type of voltage is specified, we can directly determine U effective. Knowing U effective and we have I effective, we can determine the electric power. Then let's proceed. Now, as for number 1, they are telling me calculate U effective. U effective can directly be calculated from UM using the following formula. The value of UM is given by 310 and the value of square root of 2 is given by that. And plugging this fraction here, we must be careful. We need to use the decimal value given of radical 2, which is the approximation and not the complete or the value given by the calculator. Now plugging this fraction on the calculator, then U effective is given by 219.24 volts. Then U effective is equal to 219.24 volts. Now as for number 2, they are telling me to calculate the electric power P consumed by D, and the electric power by definition for an AC source is given by U effective multiplied by I effective. So no need to construct a triangle for this formula because this is the quantity that we are interested in calculating. Now the value of U effective is given by 219.24, whereas the value of I effective is given by 0.5. Plugging this expression on the calculator, then the value of P is given by 0.62 watts. Why watts? Because U and I are expressed in the SI, which is given by V and A respectively. Then the value of P is given by 109.62 watts. Now let me move to the other section, which is section number 18, also exercise 7 as a direct application or as a problem on what we have explained so far in this chapter. So they are telling me an oscilloscope visualizes the waveform of document 1. They mentioned document 1. Now we can use it. So this is the wave that they are talking about, which represents the variation of the voltage U delivered by an AC voltage source. So why the variation of the voltage U? So notice that always axes in physics are labeled by physical quantity. This is the time t, and this is, so suppose that we don't know the labeling of the axis. One way to know is by referring to the scale. So notice that here the scale, they are telling me along the y-axis we have volts and along the x-axis we have time. So this is labeled by voltage, this is labeled by time. But moreover, if we refer to the title, they are telling me represents the variation of the voltage U. And the first one that comes after the variation represents the quantity of the y-axis. Now a lamp L with the following indication to 120 volts is connected directly to the source. Now in number 1, they are telling me indicate the type. So okay, sorry. Before we proceed, the trick in solving such type of exercises is to extract the values of x and y of this wave, because we know that any wave is described by 2 points. So let me say the value of x here. Let me write it down here. And the value of y here. So notice that what does x represent? X represent the number of divisions between 2 consecutive peaks. Eventually here we don't have 2 peaks, so we cannot count the number of divisions from the peak. Then we need to count them from the center. So we choose a point, skip a point, and we choose another point. So in this case, notice that this waveform spreads horizontally along the screen of the oscilloscope, and we know that the total number of divisions of the screen of the oscilloscope is given by 10. And let's check by counting them. We have 1, 2, 3, 4, 5, 6, 7, 8, 9, 10. Therefore, x is given by 10 divisions. Now, what does y represent? Y is the number of divisions from the center to the maximum point displaced by the curve or the waveform. And as you can notice that in this case, this wave, so if this is 1, this is 2, and this is 3. So here it's a bit tricky, but notice that the point here on the wave exceeds the value 3. So it's either 3.1 or 3.2. Since here we don't have any dotted line to represent the value between 3 and 3.2, so this is directly 3.2. Moreover, if we take the ruler and we try to horizontally project this point along the y-axis like this, and then we zoom in, we can see that the value of this peak is exactly 3.2. Okay, so in order to obtain the correct value, one can always choose use the ruler and hold the ruler exactly to be horizontal, which is parallel to this line, then shift it upward and check this point corresponds to which value. Okay, now in this case y is given by 3.2 divisions. Okay, now moreover, it is also convenient to extract the vertical sensitivity and the horizontal sensitivity, which is indicated here. So this is the vertical is indicating SV is equal to 100 volts. In this case, this arrow represents one division, so this is per division. As for SH or VB, this is given by 2 milliseconds per how many divisions? Per 1 division. And we know that millisecond is not the SI unit of time. In order to convert from milliseconds to seconds, we divide by 1000, then this is given by 0.002 seconds per division. Okay, yet we didn't start solving the exercise, but now extracting this value will make the task easier. Now in number 1, they are telling me indicate the type of the voltage U, and by indicate it means that we need to state with a justification. The type of the voltage can be determined by referring to the figure. So notice that it varies with time. If this is U and this is T, so it's not constant, it varies with time. Let me write, since it varies with time, let me say varies with respect to time, and notice that part of the curve is above the x-axis and or part of the curve is above the t-axis and part of the curve is below, which means it's positive and negative, and it is alternately positive and negative. And the shape of the curve is given by sinusoidal. Then it is AC sinusoidal voltage source. So usually whenever they ask us about the type of voltage, we need to indicate whether it's DC or AC. After we have justified why it is AC, we need to mention the shape. Here in this case, the shape is given by sinusoidal. Now in number 2, they are telling me, referring to document 1, calculate the maximum voltage UM. So, okay, sorry, no. In number 2, they are telling me draw an electric circuit representing the source U, the lamp L, and the connection of the oscilloscope. So the type of the voltage source is given by AC. So this is the symbol of the AC voltage source. Now connected to this source we have the lamp L. So this is the lamp L. So in this case we have a closed circuit. And they are telling me to show the connection of the oscilloscope. So this is the oscilloscope measuring the voltage across the lamp. Here it's not important the orientation of the phase and the mass terminal. So for example, we can place the mass here or the phase here, because in AC voltage sources we don't distinguish between the positive pole and the negative pole. Now in number 3, they are telling me, referring to document 1, calculate the maximum voltage UM, which is given by SV multiplied by Y. The value of SV is given by 100. And the value of Y is given by 3.2. Plugging this value on the calculator, then the value of UM is given by 320. Since both of these are expressed in the SI, so the value of UM will be in the SI, which is volts. Then UM is equal to 320 volts. Now in 3.2, they are telling me to determine the period T. So the period t is expressed in second, which is related to the x-axis because the x-axis is labeled by time, which is second, and eventually it's given by VB multiplied by x. The value of VB in the SI is given by this, and the value of x is given by tan. Then plugging this on the calculator, then the value of the period is given by 0.02 because everything is expressed in the SI, so the value of the period will be in the SI, which is seconds. So now, because we have determined the maximum voltage and the period, we expect that they will ask us about the effective voltage and the frequency, for example. And indeed, in part 4, they are telling us deduce, and by deduce it means that we need to use the previous parts to determine U effective, which is equal to UM divided by square root of 2. Now the value of UM is given by 320. Regarding square root of 2, so if you notice that they didn't give us the numerical value of square root of 2, so it's kept as a square root of 2. Now plugging this on the calculator, then this is given by 226.27 because UM is expressed in volts, so the value of U effective will be in volts. Now in 4.2 they are telling us also to deduce the frequency, and by deduce it means that we need to use the period. So we know that the frequency and the period are related by the following formula. Then 1 divided by 0.02, which is equal to 50. Since the period is expressed in the SI, which is seconds, then the value of F will be in the SI, which is hertz. Then F is equal to 50 hertz. Now in part 5 they are telling us, does the lamp L functions normally? In order to describe the functioning of the lamp, we need to compare the applied voltage to the rated voltage. The rated voltage of the lamp is given by 220. So because this is an AC voltage source, it's being characterized by two voltages that are given by UM and U effective, but we always consider the applied voltage to be U effective because it is the one that makes the effect. Okay, now notice that here the rated voltage is given by 220 and the effective voltage is given by 226. If we need to follow the definition, 226 is greater than 220, so we ignore UM because UF is the U effective, it is the one that makes the effect. But notice that 226 is greater than 220, but this doesn't mean that the lamp will function strongly or burns out. Because the difference, which is 6 volt, which is very small, notice that 226 is almost 220, which makes that the lamp L will function normally, okay? Whenever the difference is too small, then we can say it's functioning normally. So here I'm talking about difference 6 volt compared to 220. But if you consider, for example, 6 volts or 9 volt, in this case the difference is big, which is 3, because we are talking about small numbers. Now let me say that since the applied voltage is almost equal that is 226.27 volts is almost equal to 220 volts, then the lamp L will function normally. Okay, now this is it for part 5. What about part 6? They are telling me we replace L by an ohmic conductor D with the following indication: 150 volt. Does this component D functions normally? Explain. Now the applied voltage remains 226, but now the rated voltage is reduced from 220 to 150, and in this case the applied voltage is much greater than the rated voltage, so the component D, or the ohmic conductor, may burns out or function strongly. So since the applied voltage is greater than the rated voltage of the ohmic conductor D, and this is because 226.27 is greater than 150 volts, then the ohmic conductor D may function strongly or burns out. And by this we have finished solving this exercise. So that's it for me in this video, guys. In part 4 we'll complete solving exercises on this chapter.